Hi, the lesson today is about limits of functions, and at the end of this lesson, you should be able to evaluate limits of functions intuitively, graphically, or analytically. The most basic use of limits is to describe how a function behaves as the independent variable approaches a given value. For example, if we want to investigate how the function f of x given by x squared minus x plus 1 behaves as x values get closer and closer to 2, then we can do it intuitively, graphically, or analytically. Intuitively, we investigate the behavior of f of x values as x gets closer and closer to 2 by assigning values to x. This can be less than 2 or greater than 2. So for the function f of x equal to x squared minus x plus 1 and choosing x values as shown in the table, if we pick on x values that are less than 2 but are made to move closer and closer to 2, the corresponding f of x values are observed to be increasing towards 3. If the x values are those that are always greater than 2 but are made closer and closer to 2, corresponding f of x values are observed to be decreasing towards 3. So at this point, we conclude that the limit of x squared minus x plus 1 as x approaches 2 is 3. The limit of a function f of x as x approaches a can be investigated graphically by observing how the points on the curve would be moving as x approaches a. So for our function, the curve of which is given by the red curve, we take note that at x equal to 2, the point on the curve correspondingly has f of x value of 3. As we pick on x values greater than 2, the points on the curve are positioned above this point. And if we make the x value moves closer and closer to 2, the points on the curve tend to move downward, getting closer and closer to this point. Therefore, we observe that f of x values are decreasing, and these are decreasing towards 3. If we pick on x values that are greater than 2, the points on the curve are positioned below this given point. However, if we make x values get closer to 2, then the points on the curve move upward, getting closer to this point. Hence, we say f of x values are increasing, getting closer to 3. At this point, we can conclude that the limit of f of x as x approaches 2 is 3. Analytical investigation of the limit of a function can be done using some basic theorems. If we let a and k be real numbers, and that the limit of k as x approaches a is k, and the limit of x as x approaches a is a. And if we have a real number, and suppose that the limit of f of x as x approaches a and the limit of g of x as x approaches a exists, and that the limit of f of x as x approaches a is L sub 1, and the limit of g of x as x approaches a is L sub 2, then the following theorems would hold true. That the limit of a sum of function f of x plus g of x as x approaches a would equal the sum of the limits of each of these functions as x approaches a given by L sub 1 plus L sub 2. Dealing with the limit of the difference of functions f of x minus g of x as x approaches a, we had that equal to the difference of the limit of f of x as x approaches a minus the limit of g of x as x approaches a, or we have L sub 1 minus L sub 2. For the product of function f of x times g of x, the limit of the product f of x times g of x as x approaches a is equal to the product of the limits of each of these functions, so that we have L sub 1 times L sub 2. the limit of the ratio of f of x divided by g of x as x approaches a is given by the limit of f of x as x approaches a divided by the limit of g of x as x approaches a, or we have L sub 1 divided by L sub 2, provided that L sub 2 is not equal to 0. And for the nth root of f of x, the limit of the nth root of f of x as x approaches a is equal to the nth root of the limit of f of x as x approaches a, or we have the nth root of L sub 1, provided that L sub 1 is positive whenever n is even. Now, these theorems would hold true for one-sided limits, be it evaluating the limit of f of x as x approaches a from the right or from the left. Okay, at this point, we will be evaluating limits of functions and we will be applying the theorems that we have just discussed. So let us now evaluate the limit of 4 minus x times 5x minus 2 as x approaches 3. In this given example, what we have for the function is a product of two factors, 4 minus x and 5x minus 2. So when we are to evaluate the limit of 4 minus x times 5x minus 2 as x approaches 3, we will be applying the theorem to evaluate the limit of a product. Hence, we have now the limit of 4 minus x as x approaches 3 times the limit of 5x minus 2 as x approaches 3. In evaluating the limit of 4 minus x as x approaches 3 or of 5x minus 2 as x approaches 3, we will be applying the theorem on how to evaluate the limit of a difference. And therefore, this will now give us the limit of 4 as x approaches 3 minus the limit of x as x approaches 3. As to the other factor, we will have the limit of 5x as x approaches 3 minus the limit of 2 as x approaches 3. Okay, and applying now the theorem on the limit of x as x approaches a being a, and that the limit of the product is equal to the product of the limits, then we will now have limit of 4 as x approaches 3 to be 4. The limit of x as x approaches 3 is 3. As to 5x, the limit as x approaches 3 will just be 5 times 3. And for the last term, the limit of 2 as x approaches 3 is 2. So simplifying this, we have the limit equal to 13. If you observe what we have done in evaluating the limit of the given expression or the given function, what we did was just to substitute 3 in place of x. And if we will do that, then 4 minus x times 5x minus 2 will now be given by 4 minus 3 times 5 times 3 minus 2, or we also have 13. Okay, so at this point, we say the limit of the product 4 minus x times 5x minus 2 as x approaches 3 is 13. Okay, let us work on another example, evaluating the limit of t cubed plus t squared minus 5t plus 3 divided by t squared minus 3t plus 2 as t approaches 1. If we will be substituting 1 in place of t in a given expression, then the limit of the ratio would lead us to having a 0 divided by 0. This is not acceptable as a limit, and this is referred to as an indeterminate form. To be able to come up with a conclusive result, what we need to do is to transform the given fraction by reducing it to lowest terms. The reason the limit is a 0 divided by 0 form is because both members of this fraction have a common factor, which is t minus 1. So a complete factorization of the numerator and the denominator would show you that t minus 1 is a factor. So you can now simplify this ratio, dividing both members of the fraction by t minus 1, reducing the fraction to this form. t plus 3 times t minus 1 divided by t minus 2. And if it is used to evaluate the limit as t approaches 1, then this will give us a limit of 0. So at this point, we conclude that the limit of t cubed plus t squared minus 5t plus 3 divided by t squared minus 3t plus 2 as t approaches 1 is 0. At this point, we define what a limit is. Let f of x be defined in some open interval containing a, but possibly not defined at a. If f of x can be made as close to L as x is made sufficiently close to a, but not equal to a, then we say that f of x approaches the limit L as x gets closer and closer to a, and is denoted by the symbol read as limit of f of x as x approaches a is L, where L is a finite real value. Provided that the left-hand side limit, which is the limit of f of x as x approaches a from the left, is L, and the limit of f of x as x approaches a from the right is L. In summary, the limit of the function f of x as x approaches a is some real and finite value L, that is, the limit of f of x as x approaches a is L, provided that the left-hand limit and the right-hand limit of the function are both equal to this value L. Furthermore, the limit of a function f of x as x approaches a can be evaluated intuitively, graphically, or analytically.